Hello and welcome back to HK Academy. In this video, I want to step back and answer a very fundamental question. What is a Type 3 compensator and why is it so widely used in power converter control loops? You will often see Type 3 compensators mentioned in buck, boost, and isolated converters, but many engineers use them without a clear intuition for what they actually do. Here I will focus on the structure of the Type 3 compensator, its transfer function, and the characteristic body shape it creates. This is not a full design or tuning tutorial. The goal is to build the intuition so that when you later design or automate a compensator, you understand why it works. In most voltage mode control systems, such as buck, boost, or isolated converters, we can't directly achieve both stability and fast transient responses with a simple proportional integral or PI controller. The power stage itself introduces additional dynamics from inductors, capacitors, and PWM delays that reduce phase margin and limit bandwidth. The Type 3 compensator extends what a PI or Type 2 controller can do. By introducing two phase boost zeros and two high frequency poles, it allows a much higher crossover frequency and faster response while maintaining adequate stability margins. The Type 3 compensators aren't just a theoretical concept, they are used everywhere in practical power electronics. In voltage mode buck converters, they provide a high bandwidth voltage loop needed to maintain tight regulation during sudden load steps. In boost converters and PFC pre-regulators, the Type 3 allow the loop to track the reference voltage accurately over a wide range of input and load conditions. You also see them in isolated DC to DC converters, where the voltage loop on the secondary side relies on the additional phase boost to remain stable. Beyond that, Type 3 compensators are standard in telecom power supplies, automotive ECUs, industrial controllers, and many modular DC to DC converters. Whenever a design requires high bandwidth, low output ripple, and strong dynamic performance, the Type 3 compensator is the default choice. Before we look at the body plots, let me clarify one more important point. I'm not focusing here on how these pole and zero frequencies are chosen, only on what role each one plays in shaping the loop response. This is the analog Type 3 compensator schematic implemented using an operational amplifier and an RC network. On the left, you can see the standardized transfer function form that you will find in textbooks, TI application notes, and classical loop shaping literature. The first zero, omega z1, provides the initial phase boost. The second zero, omega z2, continues this phase lift as we approach the crossover frequency. The pole at the origin, omega p0, acts as an integrator and ensures zero steady state error in the voltage loop. The two high-frequency poles, omega p1 and omega p2, control the high-frequency gain roll-off and help limit switching frequency noise. Now, looking at the body magnitude and phase for this example, at low frequency, the pole at the origin creates the familiar minus 20 dB per decade slope. The first zero flattens the slope and begins the phase increase. The second zero continues the phase rise, creating the characteristic Type 3 phase hump. After the phase peak, the first high-frequency pole pushes the gain down, and the second high-frequency pole further accelerates the roll-off and suppresses high-frequency noise. To help you explore these ideas further, I have made several free control design resources available on my website, including a buck converter toolkit with Type 3 compensator examples. If you would like to go deeper and learn how to design, tune, and implement compensators step by step, including digital realization on TI C2000 microcontrollers, that's covered in my full courses on HK Academy. As a small new year thank you for watching and supporting the channel, I'm offering a 10% discount on any HK Academy course, valid until January 4th, 2026. You will find the discount code and links in the video description. Thank you for watching, and I will see you in the next video.